Thank you for the reminder. Intro to computer vision. And then if you want to label your own data, which I encourage you doing at least outside of this course, because labeling your own data and building an object detector on your own use case is going to be one of the best ways for you to learn. And so it's optional for this actually during the workshop, because I have a data set that's already labeled that you can start using. But I'm going to show you how to label your data so that out of this workshop, you can bring your own data in and start labeling. What this workshop is, so hopefully it's going to be a very friendly introduction to computer vision, kind of designed with no previous experience expected, but knowing some Python will definitely be helpful when we get into code. But I will describe what's happening there. So even if you haven't done a lot of programming, I think you will get a lot out of it. We'll cover applications and basic intuition, and then we're going to jump into code. So we're not going like deep into all the theory or math or anything like that behind all the algorithms. But I'm going to give you the intuition, and I'm going to link to things so you can dive deeper on your own. And then also, like I was saying, there's a lot of tutorials that go way deeper into certain parts of the subjects, and they do a great job at it. But there's not a ton of tutorials on like quickly getting started building an object detector with your own data set. It was something that took me I feel like months when I was learning computer vision to even get to. And I don't know why it takes so long, but there's so many tutorials that teach you how to do image classification or even object detection, but not on your own data set, always with like a kind of a pre-trained toy data set thing. And I really want to get you into building stuff for your own use cases as quickly as possible. And you can't learn everything in 2 hours, at least I can't. I don't think anyone here can. But hopefully you can learn enough to get excited about computer vision and inspired to like keep learning and building projects on your own. Parts of it may feel fast-paced or challenging. That's totally okay. You'll learn a lot just by sticking through it. And then keep learning after this workshop. So I'll point you to some resources afterwards, some of the resources I found awesome for learning computer vision. And thank you to Galvanize. So I saw some people in the chat here are getting ready to go to Galvanize, but if you didn't know, they're a programming boot camp, co-working space. They do a lot of events. They also do enterprise training, so you can check them out at galvanize.com. They also have a really good free like prep course. So if you want to brush up on your Python and data science skills, it's a good resource for that as well. A little bit about me. I'm Sage Elliott. I'm a machine learning developer evangelist at Sixgill.com. We do really cool stuff with machine learning, lots of computer vision, and IoT devices. It's Internet of Things. So we do like edge deployments where you can run computer vision on some sort of smaller computer that's not necessarily connected to the internet. For about the past decade, I've worked in software or hardware, usually with startups and agencies around Seattle, Washington, and then also in Melbourne, Florida. And I really love making things with technology. And I always like to ask, is there someone here from Florida or Melbourne? There's always like one person. It's always, I don't know, just kind of funny. You can stay connected to me at sageelliott.com. LinkedIn is just Sage Elliott, 2 L's and 2 T's. I love helping people get started in just programming in general, computer vision. If you're looking for a job, ping me. About you. So normally I'd love to have you introduce yourself here, but typically with these workshops, RSVPs are pretty high, and it would take a long time to go through everyone. So I just always say communicate in the chat. Where are you watching this from? Why are you interested in learning more about like computer vision, machine learning? I'm from Seattle, and I'm presenting this from Seattle right now too. Oh, and let me bring this up. So if you do want to talk more, so I love doing in-person meetups, right? Like hanging out and talking with people more. I have a Slack channel that I made essentially for this because I was doing these workshops. And if you want to go in there with everyone, there's an introduction channel. You can introduce yourself, and it's also just a good way to stay in touch. So if you do have any more questions around computer vision or you need links to something again, you can ping me in there as well. And no one said where they're watching this from. No, there's someone. I think a lot of people before we started actually said where they were watching from, so maybe they don't want to watch it again. So it said Milwaukee. Awesome. It's so cool seeing where it runs from. Oh no, they said the Slack link is no longer valid. Let me grab that link for you real quick. I should be valid in here. I even tested it earlier today and thought it worked. Let me know if that works for you, or it doesn't work. It shouldn't expire. There's that new link, that should work. Sorry about that. All right, cool to see where everyone is watching from. And also one thing, so it's kind of a galvanized hack reactor thing where you can do thumbs up as like lowercase b and d and thumbs down as like q and p. And it's a quick way to communicate in the chat of like, does something make sense? Does it not make sense? So I might ask you kind of yes or no questions sometimes. And instead of writing yes, you could quickly say B. So if you see people putting B's everywhere, that means thumbs up. It can be really confusing if you don't know that and you're like, why is everyone saying B? Setup again, just for anyone who just arrived, we're just going to be using a modern web browser like Chrome, and then a Google account because the tool that we're going to be using is made by Google and you'll want to save it, a copy of it in your Google Drive. And then if you want, you can download HyperLabel to do labeling. So what is computer vision? It's a pretty big field, but I would boil it really just down to how computers gain understanding from images or videos. There are other types of data as well that people might clump in there. Like if you've seen LiDAR video, it looks like a whole bunch of different points and it's kind of like a 3D structure. That could also be considered computer vision. Here's an example, like this is truck driving. These trucks are standing still. This is being classified as a different color because it's moving. So this is a moving truck. And you can see there's a couple of frames where it thought it wasn't moving. And it's drawing these kind of bounding boxes around it. And then you can actually see it. The entire truck is segmented out where there's kind of like a red mask drawn around it. So in this case, the computer vision algorithm knows what a truck is, and it can draw a box around it, like the coordinates in the actual image or video itself. Why I love computer vision. So I think it's a field that's really, really cool because it's pretty cutting edge. It's doing amazing things. Not just cool things, but they're actually doing really amazing things that are useful to many industries today. So like the medical industry, for instance, using computer vision to read x-rays, help with diagnosis is pretty amazing. Who uses computer vision? So more and more companies are using machine learning and computer vision across just multiple fields. So here's just a few examples that you've probably kind of heard of already. So you have Amazon. Has anyone been to an Amazon Go grocery store or an Amazon Go store before? We have several in Seattle, and I think they're going in other cities. I know they're not everywhere yet, but has anyone been to one of those yet? They're really interesting. You go and you look up, and it's just an array of a whole bunch of cameras, and there's no cash register. I don't think they really rely on any other sensors, just cameras, and they monitor you as you walk in, and they see what you pick up, and then they just charge you for it. It feels like you're stealing. So you go in, you grab something off the shelf, and you walk out, and there is like a door. You scan a QR code when you go in that, but it's really interesting. Yeah, and then I'm always worried now because I actually live pretty close to one, and I go there quite a bit, and then I'm always worried that I'm going to go into a store that isn't a Go grocery and just like walk out thinking it's going to charge me. It is really interesting though, and some of it's like pretty amazing where they didn't even want to change the way that people buy like fruit. So if you go to the Go grocery, they have fruit laying out just like they do in like a Whole Foods or anything like that, and you can rummage for the fruit you want and then take it and you get charged for it, instead of like you would imagine they want to make it easier for their cameras to detect, and they would individually bag or something, and they don't, which is pretty crazy. And they use computer vision. If you've seen them do like delivery robots, they are recently, I think they are entering the self-driving car scene because they bought a self-driving car company a couple months ago, and they also use computer vision to look at like images that get posted on Amazon for their products to actually try to do things like product fraud, like is it fake, which is pretty interesting to me. And then Google, you've probably seen like Google Photos. You could type in dog in there and it'll find all the photos of the dog that you've taken, or the pictures of your dog that you've taken. YouTube content and filtering. YouTube has, I forget what the amount is, but it's an insane amount of data that's uploaded like every minute or hour. And they use computer vision to automatically try to like filter that content out. Self-driving cars, Tesla, self-driving cars, Facebook, face tagging. You probably uploaded an image and it says, hey, is this you in this image or your friend? And I'm sure they use it a whole bunch of different other areas as well to look at data. Those are just kind of like the big company use cases you might have heard of. But I think one thing really cool, like I was saying, why I like computer vision, there's so many interesting industries that are actually using it right now with really cool applications. So some of these you might not have thought of before, like healthcare, like I mentioned, right? You do X-ray diagnostics, MRI scans, medicine research, manufacturing. This is actually how I got into computer vision in the first case several years ago, was building something to do quality assurance on a really complicated part. And I use computer vision to do that, which is really cool. You can monitor throughput, help with supply chain, oil and gas industry, like doing leak detection and worker safety, agriculture, crop monitoring, animal monitoring, construction, site monitoring, self-driving tractors, a lot of stuff around safety, and then image generation. So I don't know if you've seen this before, where NVIDIA has something called StyleGAN, and all these faces are fake. So they were generated on a large data set, or trained on a large data set of real people, and then it just generated a whole bunch of images that these don't actually exist. These people don't actually exist, which is pretty crazy. And if you haven't looked into GANs before, I totally recommend it. It's really fun. At least I find like generative kind of deep learning projects to be really fun because it's giving you some sort of interesting result, which is really cool. And you don't have to get as complicated or crazy as like a StyleGAN, like face generation. But you can generate just interesting images with it without too much training or work. Were there any other interesting computer vision applications people can think of or they've seen before that made them really interested in the industry? Someone said interested, the boy with the crooked teeth is generated image. Yeah, I mean, it's a lot of it's based on the data set. So, probably not everyone has straight teeth in the data set, but it is interesting, right? It picks up on those like stuff like that. Yeah, is there any other industries like this, is by no means an exhaustive list. These are just some of the ones that I like to point out that people don't always think of. Like agriculture is a really big one. And people don't think of farming as like a tech field or using computer vision in, but there's a lot of really good use cases for it. Oh, someone said Boston Dynamic robots. Those robots are really cool. I think a lot of the control in them, from what I've heard, doesn't use deep learning. Like they do a lot of the like kind of very manual programming right now. But I'm sure they are using computer vision to like have it walk around things and stuff like that, which is pretty interesting. And they're like some of the coolest robots I've ever seen. If people haven't seen Boston Dynamic robots, you should look them up. They have the Spot Mini, which is like the dog one you've probably seen around the internet, and then Atlas, which is the humanoid one that can do like a flip, which is pretty crazy. So it said radiation, oncology related to medical imaging. Yeah, that's awesome. Really cool. And someone said, I think they found a way to identify tumors this way. Yeah, there's been a lot of use case around radiology and medical imaging. Any other cool things? Is there a field out of this that you thought was really interesting or that you're excited about? So it's a chip fabrication process. Awesome. I'm not super familiar with that. I'm assuming that would be under some sort of like manufacturing, right? Like a CPU type chip, unless you're talking about potato chip, which you could also use. Someone said Sophia, the AI robot, they can accommodate her response according to the facial input of who is talking. Yeah, Sophia is pretty interesting robot that does an interesting combination of using like deep learning as well as other techniques. And yeah, it's like you're saying, can accommodate the response according to a facial input. So if I'm assuming like looking at my face, you can see if I'm angry or something like that, right? And accommodate the way you talk. Someone said Elon Musk neural links. I bet there'd be some really interesting stuff around there. Someone said pose estimation. Yeah, that's a cool use case. And we'll actually get to that in a second using pose estimation. All right, so computer vision and deep learning. Computer vision isn't always tied to deep learning, but in the past decade or so, deep learning in the field of computer vision has been kind of dominating the really complex problems. So every time you see something like winning a competition or something really crazy that's deployed from a large company, it probably is using deep learning behind the scenes. But I do want to make the distinction because computer vision can really just be about looking at an image from a computer in a different way. It doesn't always have to be deep learning. But deep learning is by far the most probably prominent thing for things like Amazon Go, right? Something really complex like that. And essentially, I'll put these links in the chat if you want to look at this. Essentially, what deep learning does is, in this case, the supervised deep learning, we give it a whole bunch of images, let's say like of cats and dogs, and then the label saying, you know, this image is a dog, this image is a cat, and then we pass those images into our deep neural network, and then it'll adjust the parameters so that when we feed it an image of a cat that it's never seen before, it should make the prediction that yes, this is also a cat or this is a dog. And I want to mention transfer learning. So with most popular deep learning frameworks, you can load pre-trained weights into your network. So if you're using something like PyTorch and TensorFlow, we'll talk about in a second, they all come with pre-trained networks or models. And these are trained on a whole bunch of different objects and animals. And instead of you starting from scratch, like if we're going to train an object detector and we're going to train it on geese, which is what we're going to do in this case, but it could be any object. But instead of starting from scratch, which might take forever, we can use something called transfer learning, where we take some already pre-trained weights and then we train it. We just adjust those weights that are already there on new data, and it actually works really, really well for most types of data, because it ends up that like if you have a network that's been trained for hundreds or thousands of hours on like thousands of images, that a lot of the things that it learned about other animals might relate to the new animal that you're going to feed the network, in this case, geese, right? So it might already be trained on birds and humans and able to understand what all these shapes are. And then we're just going to say, hey, now adjust all those parameters that you did while you're trained on that, and then only predict, in this case, geese or something. So you can really just think of it right now as not starting from zero, because when we make our object detector today, it's going to be surprisingly fast. And the reason why is because we're using something called transfer learning. A good rule of thumb for hobby projects, so if you're using transfer learning, is start with a minimum of 200 images or instances of the thing you want to predict, and kind of see how it does. So it will really vary depending on what your data is, how similar it is to the weights that are already in there. But that's been kind of my general rule of thumb, is like, do I want to see, or can I see how well this works with just 200 images? And typically you can get pretty good results. Without transfer learning, you probably need to spend, or you need thousands of images and spend a lot more time training. Any questions so far? We're gonna get through the slides pretty fast, I think, and get to the labeling and the code soon, but just wanna make sure. Does everyone have a good kind of high level feeling of computer vision right now? See some thumbs up, cool. A couple thumbs up. So we're going to go into some types of computer vision. Again, computer vision is a really big field, and we're going to focus on computer vision with deep learning in this case. And many of these types can be combined together or used with other algorithms to form different outcomes. So I'll talk about it as we go, and then when we actually train our model, I'll kind of talk more about how you can combine things together to get different results. So classification, this is probably where either you started before, or if this is your first time doing computer vision and you're going to go into some other computer vision course, this is probably where they're going to start you out at. You're going to feed a whole bunch of images, like I was saying, cat or dog, into a neural network, and then train it on to classify. Is this a dog? Is this a cat? And it can be really good for a lot of use cases, but also it gets tricky if, let's say, you have a cat and a dog in an image, right? And it's only trained to make predictions of cat or dog. So it can get confused pretty quickly if you're doing kind of more complicated classification or detections. And like I was saying, most tutorials will start here and really cover this thoroughly. And it's great to understand, but we're going to focus more on the object detection side. So object detection can classify and localize where an object is inside the image or in video. And this is what we're going to make today, and cover how to make one with your own data set. So here, right, and instead of just saying goose, like the classification would say, hey, there's a goose in this photo, this is actually drawing boxes where the geese are. So it understands that this is a goose and this is a goose, and then where they are in the photo, and draws a box around it. And you could train this on multiple objects too. So you could have, you know, detecting geese as well as ducks, and it could also, let's say a duck was right here, you know, it could have a duck and then draw a box around it and classify it as a duck as well. And it does use a classifier as part of the algorithm to do this. Someone asked me a question: what happens if you have less than 200 images? So we're referring to like the rule of thumb. If you have less than that, it's just that your model may not be able to make good predictions on new data, but it might be able to. So you could totally try it. It doesn't hurt anything. It's just that you might not have good results. So if you have, typically the more data or images you feed your model, the better it's going to perform. But if you have less than 200 images, it just may not perform that well on new data. Like maybe it won't really pick up what a goose is, or it'll make a whole bunch of different like misclassifications. And that's really the only thing that will happen. Nothing worse. As long as you're not using it in a real world scenario where something bad could happen, like a self-driving car. And we have instant segmentation. So this is similar to classification, except for like you can kind of see this bounding box around the bottle here, but inside of that, it's actually segment out where the bottle itself is, not just a square. So with the geese, right, we only draw a square around it. This case, we actually have like a whole mask of where the actual object is. And so these are a little bit more precise, and you could do interesting things like you could have water in here, which we're also doing a mask on, and then measure like, well, how full is the bottle with water in it. And then you have feature point clustering, or you can use this for like facial key points. So you could do something like mood. You can also do pose estimation in here. And skip over here. So this is actually classifying like what yoga pose these people are in. And you can see that there's different kind of key points of like where their skeletal structure is, and then it will change the classification. So common for pose detection like this, and then like I was saying, facial features. So if you want to see like mood or people smiling or anything like that, it's pretty common for that. Image captioning. This is pretty interesting, where you can train a neural network not just of like what objects are in here, but kind of some context around it. So if you had a network trained for image captioning, in this case, you could feed it this image, and you would get a prediction of like child flying kite on a beach, instead of just like child kite beach. It actually has some awareness of like where a kite and a child are. And then GANs, I briefly mentioned these before too, where you can do the generative adversarial network and do generative images or generate images. And copy this link. This is actually, I did a fair amount of work on GANs before, so if you're interested in that, let me know. This is kind of just some, this is actually in the process of, I was working on this project with this architect, and we were creating something to generate a whole bunch of housing designs. And this was actually just before it actually looked like a house or anything. You can go to that link that I posted if you want to look at the results. But this is actually kind of in between it actually starting to look like a building, but I thought it looked like really cool art. Just catching up on comments real quick. Someone said, how does it tell where the water level is at or how the pose is? So the model gets trained on like what water looks like or what key point looks like. Maybe the better example is the water. And we'll go through kind of when we train it and label, I think you'll see a good example of this, but it's classified this as water. Like if we didn't have the mask on here, we could still see something that would look like water. And just the network is really well trained to see what water looks like in a bottle and to see what a bottle looks like. And then it draws the mask around it. Hopefully that helped. If not, I think when we get into the labeling process, it'll make a little more sense. Someone said, tried GANs a few months ago, getting the discriminator to not overwhelm the discriminator and vice versa was way harder than I thought it would be. The discriminator and the generator, right? Yeah, that's really interesting, and that's why GANs are hard. I use something called a WP, or no, I forget. It's a WGAN, the Weiser GAN with a gradient penalty that actually ended up working best for us. There's a whole bunch of different kinds that you could experiment with. So it said, do you have any suggestions, comments about transfer learning when your images are not similar to the pre-trained images? For instance, using the COCO data set, 3D perspective weights for images like Potsdam data. I haven't looked at the Potsdam data, 2D satellite, but in general, using the transfer learning, so I did say like if it's similar to it, in general, even if your data isn't similar to it, it turns out that transfer learning, at least in my experience and everything I've read so far, generally works well across a lot of different data. So even if your data looks way different than anything it's trained on, like the COCO data set has 81 classes of like people and cows and different animals and objects, even if your data looks way different, it's going to have similar shapes to like the to what the convolutional neural network has learned. So even if it doesn't look like a cow or anything was trained on, just putting together those kind of early layers of the convolutional neural network and having it not start from scratch, generally it seems like it works well across a lot of data. Have you had specifically issues with it, or have you not tried yet? I mean, I'm going to keep going, but that sounds really interesting, and I'd love to hear more about it. So choosing a model. So there could be a lot of different cases for different models and like how to tie them together. But when getting started, just think about what is the problem you're trying to solve and the outcome you're looking for. So if you are, just okay with object detection and you want to localize something inside an image, that's cool. If you want to get more precise and actually see like where a paw or something from, in this case, it's like a mouse, and it interacting with like a piece of food, you might want to do the image segmentation. And then obviously if you're doing like facial features, like smiling, you might want to do the facial or the feature key points and like pose estimation type of data or models. Any questions, any other questions on these? I know it's pretty high level right now, but just wanted to make sure if there's any other questions. Someone said, what makes something mathematically convolution, and define a convolution at a high level. So I didn't open it up, but a link that I posted earlier, let me go open this up real quick, just so if you haven't seen a convolutional neural network before. So this is an example of a simple convolutional neural network, and here it can do number prediction. So I can draw a 5, and this is, so here's the input in pixels, right? All images in computer vision like this get converted into pixels. And then here, these are the first convolutions, and a convolution is really just a filter. So when you train your network, it puts various filters over your pixels, just as different ways of looking at that data. So it might do like blur, it might change the color, might do some just interesting changes to it. And then it does different things like downsampling, where this is the full input size, and then I'll downsample it. And there's different ways of downsampling, because essentially you're taking all your pixels and making your image smaller. And that means you have to get rid of pixels. And by doing that, you can do that in different ways of, like, you know, if you averaged all the if you average 6 pixels next to each other, made that 1 pixel. That's one way of downsampling. It'll capture generally like what color is the most prominent in those 6 pixels. So this is a super simple way, or super simple example of a convolutional neural network. And then it goes through another convolution here. It goes through another downsampling here, and then it goes into our fully connected kind of neural network here. And there's 2 of those, and then it predicts an output. So this is trained to predict numbers. And it looks really weird, right? Like, even if you're looking at this with your brain, you're like, what is it doing down here? But the way that the neural network has learned is that, you know, whatever is happening down here, this looks like a 5. Even though it's downsampled, and our brains might have a hard time understanding why it would look like a 5. Pretty interesting. And someone said the neural network looks like a mirror line. In this case, it's just showing a flattened line of like all the pixels coming in, and then certain ones light up, and it triggers another neuron in the other layer. And then depending on how these all get triggered, would make a prediction on that. You can see here too, the first prediction is 5, but also thinks it could be a 3. Does that make sense at a very high level? Again, don't worry if it doesn't make a lot of sense. Like, convolutional neural networks are pretty complicated. Same with deep learning. And you could easily spend way more than 2 hours talking about each individual one of those things. But just wanted to give kind of the high level concept when you get started. And they're great to learn more about. You totally should. But even when you're, most people, when you're programming your neural networks, like, you have tools like PyTorch and TensorFlow, which we'll talk about. And those actually do a lot of this process for you. You're not manually defining those convolutions most of the time. So it is certainly good to go back. And again, like, if you go more into computer vision courses or anything, they'll go a lot deeper into this stuff. But I just want to do a very high level kind of concept about it. So it says, so we went from a 2D number 5 to a flattened line to a dot to a guess of a 5. Essentially, yeah. Oh yeah, someone asked if I can post this link in chat, and I'll do that again. Yeah, so it takes all those pixels from whatever the image is that you give it. In this case, it was that 5. It does a lot of manipulations too in different ways, and it'll learn, your neural network will learn what manipulations to do to them. And then it goes into the fully connected neural network, which I'll post this in the chat again too. This is a really good example of just kind of seeing kind of like what a deep learning neural network is, and how it works a little bit. Essentially, you feed it data, it adjusts some weights inside of its function, so it knows when it sees a new piece of data that it should make a right prediction. Was that helpful? Again, I know that it's pretty high level, and we could go down the rabbit hole into any of those. But for now, if you just have an idea of like, I'm going to take data, I'm going to feed it to something called a neural network or a convolutional neural network, and it's going to learn how to look at my images and then make predictions on them. That's what really matters at the start. And then you can definitely go deeper into how all that works, and how to tune them and make up your own. But so far, the intuition is there for everyone. I see some thumbs up, more thumbs up. Double thumbs up. All right. And if it doesn't, again, if it doesn't completely make sense, that's totally fine too. You'll have kind of a high level understanding, and then you're going to keep learning about it, and then things will start clicking. But it's a lot to devour in a short amount of time. So object detection, just again, high level in a gist, because all the different object detectors work a little bit differently too. Essentially what it does is it'll find an image, or you give it an image. In this case, like this would be a trained network on geese, right? We would give it this new image of a goose. And this is kind of just at a high level of how most object detectors work, is it'll find regions where it thinks something is in the image. Like this is probably some sort of object. Like there are edges and stuff that look different than the background. Then it will run a classifier around that region. So like I was saying, classification is kind of part of object detection, but then it'll kind of run the classifier around the region. And then when it does that, kind of take a guess of where that class or object actually is in the photo. And it might have kind of several places, like it could have several predicted boxes thinking there's a goose here, a goose here, a goose here. But based on our calculations, like there's a lot of overlapping here. This is probably going to be one object or one goose, and then it'll draw a box around kind of those predicted outputs. There's a really good article here that breaks down a lot more about how kind of in general the object detectors work. In this case, the MaskR CNN. All right, and then some popular object detection methods is the single shot multi-box detectors, abbreviated to SSD, that they do object detection and they do it really fast. And then there's a really popular one called Yellow, you only look once. It also does object detection and it's also pretty fast. And then you have something called the MaskR CNN. The R is region, because this can actually do the image segmentation as well. So you do object detection, image segmentation, and this has really high accuracy, but it's a little bit slower. So it depends on what you want to do, what your use case is. Do you want something that can run a little bit slower and do higher accuracy, or do you want something that can run pretty fast? And maybe it doesn't have quite as high of an accuracy, but it does, maybe it will work for your use case and for your data. And then today we're going to use Facebook Detectron 2. And this is kind of a library that's kind of a fork from MaskR CNN, but it can do a whole bunch of really cool stuff built in. So here it shows it can do object detection. We talked about the bounding boxes. It can do posed estimation. So kind of that use case we saw before. This is called dense pose. So actually kind of reconstructs a 3D person out of the pose prediction, which is pretty cool. And then here it does image segmentation. So you can see, it's drawing exactly around where the cup is. And then this is totally blanking on the word, but it's another variation of segmentation where you also get backgrounds. So like this one doesn't have backgrounds, it just has those objects segmented, like the table, the cup, but it doesn't say like, here are cabinets or some sort of wall, or it wouldn't say sky or anything like that. But it can also do that as well. So you can see all the cabinets and walls. It does a really good job with it. So you can add a little bit more context, right? Like when we saw the other example of like captioning an image, this could be like, this is a person probably inside of a house because I can see there's a ceiling above them too. They're probably not outside. So if you need more understanding, you could use this method. It's pretty cool. I'll post this link in the chat as well. Any questions? Any questions on that so far? Now, again, pretty high level. Someone said, which line is the region? Let me go back to that image. So in here, it would probably be, yeah, like something like this pink line, or I just kind of manually drew these, so this isn't actually from the algorithm itself, but it would say, somewhere in here, I think there's at least one object or multiple objects. How's everyone doing so far? We're almost to the code, which are like the more hands-on stuff, which I think is pretty fun. Okay, thumbs up. I always like to ask, you guys are pretty quiet, just making sure. Just really want to real quick mention kind of the full computer vision lifecycle. So today, like we're going to be talking about the data annotation and then the actual machine learning part of this. but there's often more steps around it, right? Like you might have device management where you're like collecting data from sensors, managing those sensors, deployment. Once you train your model, how do you deploy this in production? Can you make API calls to make new predictions on images or videos? And then often you want to repeat all these steps to ensure that your model is robust and continues to perform well wherever it's deployed at. And so it's kind of like the full computer vision lifecycle is that. And oftentimes, if you go through a tutorial, they're only going to start at this first machine learning part. And if you're lucky, they might talk about data annotation. But there's a whole bunch to keep learning about, which is pretty cool. And we do make that all really easy. So one of the things we do at Sixgill is kind of all those steps in one platform. If you want to just hear more about that or have a demo or anything like that, just let me know. And you can email me at selliott@sixgill.com or message me in the Slack or LinkedIn. All right, so real quick, some popular Python libraries used for computer vision, just so you know what they are when you see them. So there are many that you'll probably end up using, but these are kind of going to be the top ones you'll probably see repeatedly. PyTorch did not update the description under there, or for a couple of these, I apologize. PyTorch is Facebook's kind of deep learning library that makes it really easy to build neural networks, including convolutional neural networks for computer vision. And then TensorFlow and Keras, that's Google's version of that, really popular again in deep learning. These are kind of interchangeable. Like you'll hear people prefer PyTorch over TensorFlow or Keras. I use both. I don't have a strong preference. I've been using more PyTorch lately, but you could start with either one when you dive more in. OpenCV is, someone was talking about this earlier, it's a computer vision library that is really good at like image and video manipulation. You can do manual convolutions in this if you wanted to. There's even some deep learning stuff built into it, but a lot of times you'll use it to like ingest a data stream, like for video or images, do something to it, then hand it over to a model, train that model, get a prediction kind of thing. NumPy is a great library for processing multi-dimensional arrays. And in this case, when you give an image to a computer, it ends up seeing it as a multi-dimensional array. So you have all the pixels of an image, and they have values inside of those pixels, typically of like red, green, or blue, like what color is it kind of thing. And that ends up looking like an array. We can actually probably look at one in our code a little bit. And then Pill or Pillow is another image processing library. Sometimes you'll see people use it over OpenCV, or sometimes you'll see them both used because one might have a feature the other one doesn't have. All right, image labeling. So most of the different model types we talked about take different data annotation to learn, and labeling is a huge part of computer vision that, again, like a lot of tutorials really skip over this, and I found it really frustrating when I was learning computer vision, because again, they would be like, here's how to build an object detector, and they would just use one of those pre-built, pre-trained libraries I talked about, like the Cocoa one. But really, to do anything really cool, typically you have to get your own data into the model, right? And I always thought it was going to be a lot harder to do that. And there are some like open source labeling tools that you can use, and they're a little bit harder to use. But we have a tool that we made at Sixgill called HyperLabel. You can download it for free. And it's a nice visual way of creating data labels. Let me share the link real quick if everyone wants it. You could download this and then label your own data set later, or you could start testing out right now. We actually have an online version coming soon. So if you happen to be on Linux, we don't have a version for that right now, but we're going to have a web version soon that can just work across all the different platforms. But real quick, I'm not going to spend a lot of time doing this, but just a quick overview of how to create labels for this project. So when we go through, we're going to build our object detector in Detectron 2, and you'll probably want to get your own data set to build something. So here I just hit create new project from your home screen. In this case, I'm going to call this Goose demo. I'll just hit next. In this case, I'm just going to add from local storage. So I just have a folder of images that I want to bring in. But you can also do like some from Amazon S3 or Google Cloud Storage. I'm just going to call this geese. You can call it whatever you want. Choose a folder. Go back. I have a folder here called geese small. It's kind of smaller images of geese. I just hit save, and then I hit this label schema button. These are kind of some example ones. I'm going to delete these. Now I'm going to create a new label called goose, and it's going to be a rectangle. Remember, we talked about object detection, kind of uses that rectangle, like squares around it. And that's how we want to, or that's what it predicts, and that's how we want to label it. And then if we want to do image segmentation, like the bottle example or some of the other ones we saw, we would do polygons. So this was much more precise labeling. It takes a lot longer to label like this too. But often, if you're having trouble with your model, just like not getting the accuracy you want, and you've only been doing object detection, you might want to try image segmentation, because it does tend to be more accurate. This also supports like points, feature points, like we talked about, facial, moods, or the pose detection, as well as like classification, text. You can kind of do all those different label types in here. But I have our goose, a rectangle, hit create. I'm going to hit start labeling, and then this will bring up my goose images. Some of these, they're photoshopped. There's a story behind that. It's actually in a different talk, but I want to kind of overcome limitations from a limited data set. So I took out geese and I just pasted them on different backgrounds. And in here, our label's already selected, but if we weren't selected, we just click this, and then boom, label. And you just hit submit. And you would do this for every photo. Again, I'm not going to do it for every photo here because that would be really boring for you to watch, and I already did it. But essentially, we just keep doing that for all your different images. And then once you're done, you can go to dashboard. Oops, I'm going to hit submit on that. You go to your dashboard, hit export project. And then a cool thing about this program too is you get a whole bunch of different data options. So a lot of tools, like open source ones, will only export to something like Pascal VBC. In this case, Detectron 2 does a really good job at taking a Cocoa data set in. So we want to export our project as Cocoa. And that's just a different format. So it just looks like this when it comes out, different JSON format. And I would just hit export now, choose the folder where you want it at, and then it's done. And then I would just upload that into, in this case, we're going to use Google Colab, and I'll talk about how you can upload your own version of that in there instead of using the one I'm going to give you today. Does that make sense, everyone? Is that easier than you thought it would be, making your own data set? Any questions on making your own data set? If you want to do polygons, you just select polygon here, create, go back to your labeler, and then you can zoom in, and you got it. Oops, I selected the square. And then you would select your polygon mask, and then you draw around. I'm going to do a very bad job here. You want to get as close as you can to the goose, but this is what drawing with a polygon looks like. Someone said, FYI, the clicks you're making are blurring in the Zoom presentation. Oh, interesting. The clicks I'm making? So what file type is it export as? Yeah, so it will export as JSON. And then there's an option as well where if I export as Cocoa, this is the preview what the JSON will look like. You can also click include images with JSON export. I usually do this with the Cocoa one, so then it just goes into one folder. You have all of your images, and then you also have a JSON file that your model will look at and understand what's in those images and how to draw the rectangles or the polygons around them. We'll look more at that when we bring it into our model. So it said blurring the transitions between dialog boxes. Interesting. Don't know how to fix that. Sorry if it gets blurry. Someone said helps if I pause the cursor. Was there any clicks that you want me to go over again that you feel like missed because it was blurry? Was there any other questions around labeling? Someone else said they did not see any blurriness. I'm not sure what's going on, everyone. I haven't had this issue before. Could be a Zoom thing. Again, pretty easy here. I'll link to the docs on this that actually has more visual tutorials as well. So if you just have any questions around how to do any of the other types of labeling, it's documented in there. Someone said, if I try to define data types for things that can be different colors, say plates versus bowls, should you do the labeling on one color or try every permutation of colors on plates versus bowls? You're saying, so if you want to detect plates or bowls, but you know you're going to have different color ones you need to detect, you'll want to have those colors that you know you're going to have in your data set to help it detect them. Not saying it won't work if you have different colors, because it might pick up like shapes of bowls and plates, but certainly like labeling is a huge part of machine learning in general, and then in particular with computer vision, it's so important that you actually are in the environment that you're going to do your detection. So like things like the background changing, if your model was never trained on a specific background, and then you are now trying to detect geese with people in the background or something like that, and that it never saw it, it might mistake those people as geese. There's actually, I'll link to this. So I actually have a talk kind of specifically on this, and you can go watch it. It's recorded, as well as like it's kind of like you could read it kind of like a blog post, but you could also click the YouTube link here. But it actually talks a lot about kind of how to think about creating a data set. And I won't go through the whole thing, but just as an example, I trained a model to detect geese, but it was always in this park background, right? It did a really good job in this park, but as soon as I tried to detect anything in my living room, it thought I was a goose, because we did a good job of training the model of like what was a goose, but we didn't do a good enough job of training it what wasn't a goose. So if you know you're going to be detecting things in specific backgrounds or in different variations, it's best that if you can get those variations in your data set. One way around that that I talk about in here is, because I didn't actually have geese in my living room to train this on, I just photoshopped geese out and I pasted them on images. And this is the training data shop. A+ Photoshop job. It's pretty good, right? So this is the new training data set. These are the labels from HyperLabel. This is me on vacation. There's people at Galvanize. Right now it's getting a good understanding of these features make a geese, and these features are not geese. These people are not geese. So then I think I only put like 10 new images in there, and then the results are pretty good, right? It's not detecting me as a goose anymore. It can still detect a goose pretty good. If I had one in my living room, this is just like a picture of a geese on an iPad. But it's not perfect. So if I leaned my head a certain way, still thought I was a goose, but it wasn't that sure. So you could actually cut off the confidence here, saying only detect a goose if you're like 80% sure or something like that. And it still thought this chair was a goose. I was more sure. So like labeling data and getting data to label for your computer vision program is very, very important, and can drastically change the way that your model works. So really important to think about. This is a really fun thing. Just go look at, and again, right, like if you can't get that data, you might be able to come up with some way of creating synthetic data for it, right? Like this isn't real, but it totally worked in training the model for my use case. And you could do this in a lot of different use cases. So it said, how many images did you use for geese and non-geese? And here, I think it was like, I have it documented somewhere here. It's like 100 images, but it's actually going to be, I think, the same data set. I might have added a bit more to it as the one we're going to use today. So we'll see. I think there's 116 images. A lot of those images have multiple geese though. So there's like 300 plus instances of geese. But those are great questions about labeling. And that's why you should get in, label your own data, because you learn so much when you're actually labeling data and not using something that's like curated and well done for a tutorial. When you get into the real world, it's just way more messy. Any other questions on labeling or anything like that? Someone said, can objects have multiple labels, red and plate, so it can identify more information? It depends. So there's different ways of doing it. Like you could create a label called, red plate and make a new label for each one. Or you could do a way like plate as an object. I can't type. And then you could add a sub label where then you would say like color, and we'll say select as classification. So we could say, is it red? Is it blue? And now if you were to label this, let's say this is a plate, you can label here, and then you get an option of select what color that plate is. So we can say it was a red plate. And so that's called a sub label. So you have one overall label saying this is what the object is, and then there's a sub label. This is like a sub sample of that, like red or blue. The thing with that is it doesn't just inherently work with every type of model. So I think using it with like Detectron 2, you have to do some changes to the like kind of architecture of how those things work. But you can certainly generate the labels for it and then look into how to train a object detector with a sublabel. Does that make sense, Brian? But depending on the use case too, you could do separate labels. So it says, should example pics be all the same size? I typically like to resize them. So what happens when you train your neural network is it'll automatically resize them. So in theory, you could feed it a whole bunch of different images of different sizes, and it'll always read them in at like 255 pixels, and it'll kind of squish them down. What I like to do is generally resize all the images to the same size kind of before labeling or after labeling. If you do after labeling, you have to make sure that your labels also change coordination. So typically I'll do it kind of before labeling. And the reason behind that too is like, even though your network is always resizing your images down to a certain size, if you resize them beforehand, it'll save memory and actually be a little bit faster, depending on like how much memory you have on your computer or GPU, because you still have to load those images into memory while training. So if you resize them to all like 500 by 500 pixel images, because, or in this case, like 800 by 600, instead of the default was probably like 2000 and something like a high definition image, and I don't need that for my network. So I typically kind of resize them all to the same size, but you don't necessarily need to. So it said Torch Vision has some transformers that appear to change the color outside the label area. We didn't see any that would change the color of area interest. I'll have to look into that a little bit later. Transformers. Yeah, I'll have to see what exactly you're describing there. Any other questions on labeling? Does this make sense to everyone? It's a super intuitive tool. Create a project, create your labels, and then just export to whatever label type you need. But does everyone feel pretty good about labeling? Someone said, just wow, HyperLabel, love. I love it too. In fact, the talk I did with the original Geese dataset on GitHub, this one, I did this before working at Sixgill, and I just really liked HyperLabel. I wanted to do a talk on it. And now I work here, which is awesome. But yeah, it's a really good one. Go kind of read more about creating a data set. And yeah, like HyperLabel, like I was saying, I really liked it before here. It's the tool that got me interested in Sixgill, just because it is a really nice developer tool. And they made it because, at least at the time, there wasn't a really good image data labeling tool, and they were having lots of issues labeling data for their projects. So they created this tool that made it a lot easier. And yeah, now it's just right now a free download. So I definitely recommend it. And all the things I talked about, though, that transfers to other tools too, like how to label. If you use a different labeling program, rectangles and polygons, they all kind of work the same. And you just want to make sure that you're exporting them to the format that you need to use them. And then coming soon, so we have some cool features coming soon too, like labeling there. But some stuff that will be coming soon is like ML assisted labeling, like automatically train on what a person is and drawing those polygons automatically, because drawing a polygon can take a long time. One feature I'm really excited about is actually like drawing a rectangle around an object, but then making it polygons, because I hate drawing polygons. They take a long time. Like if you're drawing around a person, it can take, you know, like a minute versus like a square is just, you know, seconds. Cool. Just one more time. Just any other questions around labeling? Everyone feels pretty good with it? Are you going to do some of your self-labeling? If you do, I'd be excited to see like what you work on, or if you have any issues, let me know in that Slack channel. All right, no other questions. It looks like someone said auto QA. So you could have something like, let's say that you are labeling images of cheetahs, like that example, and your model's trained to understand cheetahs pretty well. You could automatically check your labels to make sure that you're not like missing a cheetah or something that it's detecting in the image. Oh, someone asked a great question. Is there a way to import video frames? Yes, it's actually built in, and I totally should have mentioned this. So you could download a whole video, just go to create project, just like you did, hit your local storage where it's stored, point it at the video. And once you do that, it'll say, hey, there's a video in here. How many frames per second would you like me to import the frames as? So you could say like 1, it would bring in 1 frame per second. You could say 10, it's 10 frames per second of video. But that's actually a built-in feature of HyperLabel, which is also a really cool feature. There's a whole bunch of cool stuff I probably didn't mention like that. Someone said, have you had experience with dirty labels? How much improvement did you gain by cleaning up the labels? I haven't had a ton of experience, I guess, personally with that, but you're like, depends on how, by dirty label, I imagine you meaning like the labels just aren't perfect, or like the polygons aren't really drawn perfectly around something. And typically you get improvement by fixing that, but it just depends on the data, the model, how kind of dirty they are. So instead, can you merge multiple rectangles and triangles to make one polygon? I'm not quite sure what you mean by merge them to make one polygon. Someone also said, are you able to label each frame in a video? Yeah, so if you import that video, like I was saying, you just enter the frame rate that your video was, and it would import every single frame in the video. Typically, you might not always want that. Like you might want 10 frames per second or something. All right, cool. I'm going to move on to the code section so we can make sure we get through it. And if you have any other questions about labeling, I'll be hanging around after that. So right before we jump in, though, just coding expectations for yourself. It's totally okay if something doesn't make sense. Learning to program in computer vision is complicated. Getting errors are cool. They're trying to tell you what's wrong, what to fix, so don't panic, and hopefully we won't really get any errors. And then just remember, you don't need to memorize everything. Just try to remember the high-level concepts so that you can kind of Google and do more research into that concept if you do get stuck or if you need it again. And then mainly just be awesome to yourself and everyone as we go through. And you can totally do this no matter what your experience is. I'm going to share this link in the chat. You'll want to open this up. And it should bring you to a page that is this. And let me know when you get here. So it should look like this, Google Colab. This is Google Colab. It's Google's way of hosting what's called a Jupyter Notebook, which is a really common tool used in like the data science industry and machine learning. And it's a way of combining like code and documentation and visual output in one place. All right, once you're here, hit File and save a copy in Drive. It might take a minute creating a copy. And then it should pop up in a new tab. Sometimes I've had it bring up like a prompt saying like open in a new tab, and then you have to do that. And then let me know when you do that, because everyone needs to do this to run all the code. Otherwise, you might have an issue. So File, save a copy in Drive. And while everyone's doing that, just a quick intro to Google Colab. So this is a text cell. You could double click on this once you have your own copy. You can write whatever you want in here. To get out of this, oh, someone said the Slack channel is no longer active. I did paste the current active link in the chat. Let me do that again. It's possible that it's not in the notebook. Someone said this worked. Oh, someone sent me a private message saying that. Let me know if that doesn't work. This should work. If not, I'll have to look into this. Does that Slack link work? Okay, said yes, it works. Okay, cool. Yeah, sorry about the one in the slides. I think was an old one that expired. Someone said, did I exit the notebook in Colab? I did not. So you should have a copy in your drive. Once you're here, like I was saying, this is text. You can double click on it. To get out of this, you can hit Shift Enter. And all right. Did people say save their own copy in the drive? One thing to note here too is a really cool feature of Google Colab is they give you free GPU time. So if you go to runtime, change runtime type, you can look in here. Yours should be selected to GPU because you made a copy from mine, which already was selected from a GPU. But if it's not, then you'll want to hit this drop down and hit GPU. And GPUs are what's usually used in like deep learning and computer vision to train a model. It trains it way faster than just using a CPU. And then this is what a code cell looks like, this little gray box. You can hit this play button to the left of it, and you'll see it'll take a minute as it's connecting to the resource. The first time you run a code cell, it can take a minute to run, but once you run your first one, everything should run pretty fast. Was everyone able to hit this? There shouldn't be any output, but if you hit this play button and it runs, then you know that you're good and your notebook is going to operate well for the rest of the workshop. Say thumbs up. Everyone else is good. Anyone need me to go over anything again? Also, I know occasionally some people come in late and ask for the link to the notebook. If someone wants to monitor the chat, if someone asks for the link and share that link, that'd be cool. All right, so you're able to run this code cell. So can this be exported to Jupyter Notebook outside the Colab? Yes, it can. So if you go to File, you can hit download as a IPYND. That's actually the Jupyter Notebook extension. So you can run it locally on your machine as well. Yeah, no worries. All right, is everyone good? Last chance to say you're not good before I keep going. Someone asked if I typed a 1 or an L. Not sure where that was. Oh, I didn't type that at all. It's just saying 1 because if you have multiple rows, it'll put a number there. Yours, it's possible yours might not have the number because it might be a setting in Colab, and it's possible I changed it a long time ago. But I didn't actually type anything. It's just an empty code cell here. But if we wanted to do some Python, and we could print hello, run it, and then we get the output here. So it's a really cool tool. You can put code here and kind of get output below it, as well as like write in documentation. All right, I'm going to keep going unless someone says something's not working or they're not ready. All right, first thing we want to do is just install some dependencies here in the notebook. So run this cell. If you don't see me click on the play button, I'm hitting Shift Enter, and that plays that code cell or runs that code cell. And we just want to check our version. So if something breaks in here later for you, like if you come back a few weeks or months later and this notebook isn't working, it's possible that the PyTorch version got updated inside Google Colab. And you could probably fix that by uncommenting out this code and reinstalling PyTorch 1.6. So in this case, I always like to print out what version this is. We were expecting 1.6 in this case, so we were good. And then I'm going to run here. And this is going to take like a minute to install. This is actually installing Facebook's Detectron 2. So I said what to do after the code cell. After this code cell, you don't need to do anything except for just keep running these other code cells. So here we're installing all of our dependencies for Facebook Detectron 2. and it already installed because a lot of the stuff is already installed. So Google Colab comes pre-installed with like things like PyTorch and TensorFlow, so you don't have to install those every time. But it doesn't come pre-installed with Detectron 2, but it uses a lot of the requirements of like PyTorch, so it's already there, so it installs pretty fast. And then you'll get this error, but ignore it. Don't restart your runtime. Everything is fine. Is everyone following so far? We really haven't done too much. We're just installing PyTorch, and you may have used Python before. Pip install library name is how you install libraries into your computer for Python. And this little exclamation mark is because you can actually run bash commands in here. So if you're familiar, like ls is how you list stuff in your directory. If you just type that right now, it would throw an error at you. Oh, I guess it doesn't. It used to be you needed a bash kind of like explanation. And I think you do probably for some of the commands. This just is listing everything in the directory. Could I save this file as version 2 so we can see afterwards? Sure, yeah. I'll make sure, if you remind me to, in the chat, I can send this out in the Slack or anywhere as well. Someone said they're getting an error. Did anyone else get errors? Someone's seen an error with pill and Annotation. It looks like someone got an error. Oh, so I said ignore this error. Oh, so anything that's in here, that's fine. Just ignore it. If you get an error where like a code cell stops running, then that's when something is maybe wrong. But if we just get past these installing dependencies, we should be okay. So anything just kind of in this output, that's okay, I think, to ignore. Did everyone get to this point? Like, we're going to install here, install our last dependencies. We're going to import Detectron 2 after we installed it. Some other stuff from there that we're going to use, like the logger. We're going to import NumPy. We're going to import JSON, OpenCV, random library. Once you run this, and if you don't get any errors here, you should be okay. Someone said, any way to see the sample images and data? We'll see my sample images. I'm not sure if you're talking about the Detectron ones, but I also link, I think, to the official Detectron Colab and their like GitHub, and they have a lot of stuff like that you might be asking about. Or are you talking about our examples? So we will be looking at our data. All right, so here we're importing our libraries that we'll be using. This is just, again, kind of linking to HyperLabel and showing a quick example of using it. And then here, I would just go ahead and run these real quick, just as it installs. This is a GitHub with a link to a labeled data set. If you wanted to bring in your own data set, I talked about this right after that, is you could click this icon here and go to this little folder icon. And what I would do, and actually what I often do, is I have a Google Drive folder in my Google Drive of like data sets, and I would upload your labeled data set into that folder. And then you can hit this little Google Drive folder icon, and this will mount to your Google Drive. And it takes a minute. Then you have this Drive folder, and then you could dig down where you actually save those. So like I have an ML folder here, and I have something called run. Then I had like a strawberry data set I was working on. Then I have my strawberry cocoa saved in instances right here. This is from HyperLabel. So I did an export, and then I just uploaded it into this folder. And then in this code cell, so here we downloaded those geese examples that are already pre-labeled. This just makes it really easy to run the workshop, but eventually you want to get your own data in. So I'd mount to Google Drive here, upload your Cocoa instance into Google Drive. And then what you want to change is just in this next code cell, this is where we're creating our data set that Detectron 2 is going to use. And you would actually just want to change this line and this line to where your data set lives in Google Drive. So if I wanted to change it, get this instances JSON. I would copy that path, and then I would just replace here. You can see that this path is much longer. It goes into Drive, My Drive, wherever you stored those instances. Someone said, is there some way to see the geese dataset downloaded in Colab? Yeah, so we will be viewing those as an example, but you could also, in this kind of file explorer, you could go, you could go look at your files here, and here's that goose dataset train. You could see the list of them. Someone said they're having an error importing libraries and they see no GitHub loading links. Did this work for anyone else? Did they download the geese? So if you don't have this open yet, you can hit this little menu thing here and go to this folder, Files. And then you won't have all these files if you didn't connect your Google Drive yet. And you can see that there's a folder called Goose Object Dataset. And you could look at train and validation folders that came down. You're failing on Cocoa dataset. Let me make sure it works for mine. Oh, I think I already ran this. And so running it again, is this the error that you're getting? So it says dataset, my dataset train is already registered because I already ran that code cell once. If that's the same error you're getting, go to the next code cell and see if it runs. Yeah, it can be a little bit hard to tell when it's done. Like I just did the same mistake. And if you want to get rid of this error or any output, you can hit this little X next to it and then it goes away. So what we did was we downloaded a Goose dataset, and then we have two folders in there. We have a train folder and a validation folder. Each one of those has images and then the JSON that came from the HyperLabels. And that JSON contains all the coordinates of like where to draw those bounding boxes around the geese. And then you run this and it registers them as Cocoa datasets because they're already in a Cocoa format. And then if you run this next cell, what we're doing is essentially just reading in those data sets. And this is saying for random 3, so for data in random dataset dictionaries, which is what we made over here, we're just going to take the 3 random images from it and print them out inside Colab with the bounding boxes from the instance file. And this is really important to do, is to always check that when you read, like when you, the first time you're bringing images in to your Colab notebook or wherever it is that you're going to be training your model, always make sure that you're reading them in correctly. And I talk about this in that other talk I did too, because if you're not reading them correctly, like in this case, we're using a pre-built loader, and chances are it'll read it in pretty well. But if something is messed up in your JSON or in some way that you're reading in your JSON, you might see these boxes are going to be like drawn crazy, like all over the place. Like in this example, I think I accidentally reversed the coordinate somewhere. So it was drawing boxes like this when it should have been drawing like this. So it's really easy to do by mistake, depending on the program you're using. So every time you load in data, make sure you're seeing what you think you should see. In this case, we want to see pictures of geese with the boxes drawn around it, and then we know that our model should be able to train. Let me catch up on chat real quick. It seems like okay. So I think Tom, that fixed your error, right? You did the same thing I did. Someone said they have the Goose object data set from the notebook in Google Drive. So if you don't have that or you don't see it, again, it might look like this. There's a little bar here. You can hit this folder icon and it should look something like this. You should have these folders. You might not have this Google Drive folder. When you get this Google Drive folder, you can hit this icon. For you, it won't have the cross on it and it will mount to your Google Drive. And then you can access stuff that you save in Google Drive. So anything in here outside of your Drive folder is temporary. Like if you exit out of this and your instance goes away, everything will be lost in here. So every time you train a model and you want to reuse it, or you know that you want to always have your Goose data set be accessible and you don't want to have to download it every time, you can upload it in Google Drive and then hit this Connect to Drive button, and then just make sure that the paths here reflect the paths in your Google Drive. And the easy way to do that is go to the thing you want, and then just right click on it, copy path, and then you can paste it in. So in this case, right, we're looking just directly in content, which is right here. And then we're saying Goose object dataset train. So we're going here. But if I wanted to go in my Google Drive, then I have to get that longer drive path. But the easiest way to do it is to just hit this Connect to Drive, navigate there, and then copy that path in. Does that make sense? All right, yeah, and you'll get random images here. So in this case, this is what mine looks like, but yours might look differently. But there should be rectangles around all the keys. Was everyone able to do this? See some thumbs up? Once we're in, we're going to make some pretty quick progress. We're going to get immediately to training. So what I'm going to do is go ahead and run this cell and then come back and talk about everything that's happening, because this can take a little bit to train. This is actually where we're doing our deep learning computer vision. So just want to make sure that this is going to start up. And as soon as yours starts, let me know too. So we see some output. And again, I'll go over the code in a second. But here we can see this giant block of code, or like what looks like code or something like that. This is actually the network architecture. So when we talk about convolutional neural networks, we were saying there's like things called convolutions and downsampling and pooling and stuff like that. So this is actually kind of what the architecture of the neural network looks like. And there's a whole bunch of different convolutional layers, conv 2D, 2D convolutions for 2D images. And you'll see different parameters in here that you'll learn about as you learn about convolutional neural networks. But if you're curious, that's what all this text is. Scroll down. And this network is pretty big. So when you learn about like convolutional neural network architectures, ones like ResNet and stuff, which I think this is using, there's a lot of layers to them, and they're actually pretty big. And you might build like your own like multi-layer one at some point while you're learning, but probably not something this big by hand. We get some outputs here. You'll get a warning right here. This is totally fine. So the only reason you're getting this warning is because we're using those pre-trained weights that were trained on 81 classes, but we're going to train it only to predict one class. So we're just saying that, hey, like your one class predictor doesn't match our 81s that we were trained on. And then you can see that here it says that there's one category of labels, Goose, and there's 302 instances. So we only had 118 images, I think, but we had 302 instances of keys in those images. And then I'll go ahead and scroll up and we'll go through that code. Catch up on chat real quick. ResNet, this is happening. How get all pictures to load from Goose object dataset? We're loading them right now, I think. Oh, it's all connected to Drive on my side. I can come back. So in this case, if you just follow how the code cells are in here, but I can come back and help you load images in from Google Drive. Would you know anything about backend GPU? Curious, learn if it's comparable to something in the market. So the backend GPU, I was actually going to talk about this. The backend GPU for Google Colab varies a lot, especially if you're on the free tier. It actually doesn't matter what tier you're on. They have a pro tier, which is like $10 a month. You get a little bit better GPU. But the thing about Colab and why it's either so cheap or free is it's just like whatever they happen to have around that they want to get to at the time. So there's actually no guarantee about what GPU you will have. So sometimes you might get a really good one if you're lucky. Sometimes you might get one that isn't as good and it might take a lot longer. So it really varies. There's one thing about Colab that, I mean, it's awesome because it's free and or cheap, and it's so cool. But it's one thing to know that it's no guarantee of what type of hardware you're going to get. Let's see, any other questions? I can always come back real quick, but I'm going to go through this just so we make sure that we get through everything. All right, so here we're importing something called default trainer. This is the training method in Detectron2, and we're making a new variable called CFG configuration or config, and we're assigning it to this get config function from Detectron2. And then this is important to note. So we're doing object detection, and we're using a model, the faster RCNN. But there's different models that you can use, and you can look at what is called their model zoo. I linked to that up here. If you wanted to do image segmentation, you would want to change this out. For example, here's the image segmentation path, like for the configuration, and so you would copy that and just replace it right here. So we're doing Cocoa detection, but if you want to browse different types of models, you can on their what they call model zoo, kind of like a free marketplace for the different models that you can use. And then here we're saying our training data set, we're passing it when we configured our Cocoa data set here. We said my data set train, and that's where we're passing it as a data set to learn from. And really important, I made this mistake before. If you get rid of this comma, it's going to throw an error because this makes it a tuple data type. And that's the data type it's expecting. But if you remove it, then it isn't a tuple anymore, and it gets upset, but it's not inherently clear what it's going to upset you about. So if you do get an error and you did some changes around here, just make sure that you do have that comma there. You can have the option of doing a test data set. We don't have that implemented here, but you could, as you're training, also run your network across a separate test data set to make sure that it is improving or learning. So essentially, you're running it already on a training data set, and it's going to improve on that. But you could have a separate data set that it's never seen before, and you want to make sure that it's improving on that data set. Total number of workers. So this is if you want to scale across, I think like different GPUs, you can do that. And here 0, I think is just going to default to kind of what it thinks is best. But if you actually want to manually configure a little bit more of scaling, you can. And then here, model weights. So this is our starting weight. So remember I talked about transfer learning, and this is, again, it's the same line up here. And they should be the same. If you gave this a different model weight, it wouldn't work because these did essentially use this model on that Cocoa data set of like 81 classes, and it's well trained on all those things. So this is our starting point. So we want to load in these weights, and then we're going to learn on our images, and it'll learn much faster than if we didn't have this model weight to begin with. And then solver, I think this is just kind of some optimization. The main thing here is you'll want to change learning rate potentially. This one is usually pretty good for this type of data, or oh, I just see a lot of questions in chat real quick. So someone said define transfer learning. We talked about in the slides before, essentially transfer learning is you're using a network that's already been trained on a whole bunch of images. So your network isn't starting from scratch, and it's able to use a lot of those weights and knowledge that it's learned about images and transfer that knowledge into your new images. Yeah, essentially just think of it as you're not learning from scratch. All right, I'm going to go through pretty quickly just so we make sure we get through the rest of the code. I want you to leave with an object detector, and then I can come back and answer any other questions and go through any of the code that I go through fast here. But a learning rate is an important thing during deep learning, and while it's learning, this is usually going to be like a good default to start with. But if for some reason your network really isn't understanding your images well, you might want to change this to like a higher or a lower number. And then this is the amount of iterations, or sometimes called an epoch, that it's going to go through. So here we have 300 iterations. So it's going to look at all of our images, make adjustments to our neural network to predict a goose better. And it's going to do that 300 times, which isn't that many times. And that's because we're using transfer learning. And we're also kind of lucky because geese, even though there's different lighting and different poses, look very similar to each other though, right? Like you could look at one goose and look at another goose and maybe not tell them apart. So if you had a more complicated data set, you might need far more iterations from this too. But we're going to start with 300, and it should perform pretty well in this data set. But both the learning rate and then this max iteration are going to be two major hyperparameters that you'll want to change depending on your data set. Batch size per image. So this is going to be, as it's training, it'll load in 32 images at a time. I think by default, it's much higher, like 512. We don't even have that many images in our data set, so we just set it to 32. This really just kind of adjusts training time sometimes, but it shouldn't really affect your output. And then here, this is important too. So if you're training on your own data set here, you'll want to change this to however many classes you're trying to predict. So if you're just training on pictures of your dog and you're just doing that, then you want to stick to 1. But if you're training on dogs and cats, you would want this to be 2. So it's going to know to make 2 different predictions, a dog and a cat. Otherwise, it'll just always default to the first one that comes in on your Cocoa data set. Does everyone feel okay on these hyperparameters? So if you were to come in with your new data and just do object detection, you don't need to change this. You don't need to change this, but you would need to change your URL to your data up here. And then I would start with this learning rate and even start with this iteration just to see how your network does. And then you would want to change the number of classes you're trying to predict right here to however many it is that you want to predict. And then these are just, this is actually making a directory. So it made this directory output. And that's actually where it's going to save like our final model when it's done training. And then we just start our trainer. You have the option of like if you want to resume or load training. So if you already had a model and you didn't, like you did some training, you want to come back with new data or just train it for more iterations, you could train this to true and point to this model path. And then the trainer.train, that's calling the actual train function that's going to run through all those iterations. If I scroll down, so mine is done training. Did anyone else finish training? I see some yeses. It could vary. So if you happened, like I was saying, how you get different hardware, different GPUs, it can take a lot longer. So for me, it took about 3 minutes or less than 3 minutes. Yours could take 5 minutes. It could take 15 minutes. It just depends on the hardware that Google ended up giving you. Yeah, so someone had more than double the amount of time. So just something to keep in mind, right? That Google Colab, it's not always going to be reliable that you're going to get the best GPU. And if you do pay for the Pro version, I think you are more likely to get a little bit better one. So if it's something you use a lot, you might want to look into that. I think it's like $10 a month. It's a good option if you're doing something like deep learning or computer vision, but you don't have a good GPU at home and you don't want to pay for like Amazon Web Services for the GPU, you can kind of do this pretty cheaply. Someone said training curve section gives an error 403. Let me see. So this is what you should get. Oh, what is happening? Okay, there we go. And it should look something like this. What you'll want to look at typically is, like you can see that your class accuracy is going up. You always want your accuracy usually going up, but you don't want it going down. And you want false negatives going down. There's a whole bunch of other metrics in here. You can look at loss. Loss is something usually computed during your function optimization, and you typically want that going down. So typically you want accuracy going up and loss going down. And it looks like we are in most of these cases. Someone said they got an error loading this. Did anyone else get an error loading this? Oh, someone said they did get some pictures in code loaded, hopefully because I ran all cells, did not change any code. If you did run all the cells, it should be fine. So if you do just want to quickly run through everything, I'm going to step through it still, but you could hit run all. So if you do it right now, you ran some of the cells, you'd probably want to do run after, and it'll run all the cells, all the code cells. Your pitch, it should be, if you just hit run all, it should be. I'm not doing really any changes, but I want to talk about the changes that you can do to the code when you bring in your own data set. So no one else got an error here? Tom, you did. Can you try rerunning it? Did this finish? The training worked, but this didn't load. Interesting. I don't know why, if it's just like a tensor board error on Colab. Let's go to the next section and see if you can run the rest of the cell. So here, we could just look at the outputs. I like to look at it visually in here a lot of the times. Again, to get to it, just click on here. You can see that there was an output folder that we created, and we have something called model final path, or model final dot pth, which is like PyTorch. I forget what the H kind of stands for, but you'll see this dot pth is the model file itself. Someone said they keep getting the 403 on TensorFlow. Interesting. Someone said accuracy should be going up. So if you click through in here, or where do you see it? So if you click through in here, it's kind of hard to see in Colab sometimes. Scroll down. If we go into this fast RCNN metrics, you can see class CLS accuracy is going up and false negatives going down. It's weird that you're getting that error. I've never had that, and I've run this quite a bit, Google Colab, so my apologies. I'm not sure what that is, but hopefully you can run the rest of it, and then I would just try it again on either rerun the training at some point and see, or with a different data set. It shouldn't affect anything else we're going to do. It's just a nice way to make sure that, yes, your model did train like you thought it should, like accuracy is going up and your loss is going down. All right, so here we want to use our model that's trained now. And so here is the code to do that. Again, this is similar to like when we set up the training. We're going to say configuration equals config, and then we're going to pass parameters into that. And here we're going to say from that model zoo, we want that the same architecture that we train the model on. So this is just saying that we want that faster RCNN X101 architecture. So this is the COCO detection, faster RCNN. It's the same one that we use to train. So if you did image segmentation, then you would want to have that same model architecture that you took from the model zoo for image segmentation in here. And then we're going to say model weights before we set the model weights as the pre-trained COCO ones. But instead, we're going to put the path to our model here. So this is just saying inside that output directory here, go find model final.pth. And then if we're going to do any testing, which we're going to do here real quick, we can set our test data set to one of the COCO data sets we brought in. We did bring in that data set validation one, if you remember. And then again here, loading in a new model, you want to make sure that you set the correct number of classes. Again, we only have one class, but if you are training a model on multiple things like ducks and geese, you would change this to 2 or 3, but we want to keep it 1 right now. And then there's a threshold to show predictions. So in this case, we have it set to 0.9. So that's saying if we're 90% sure it's a goose, then we want to count it as a prediction and draw out that prediction. But sometimes you might only want to be 70% sure, so it'd be 0.7, or whatever you want it to be. It could be even 95%, and that can be important tuning to do too when you run your predictions. And then we're going to create a new variable called predictor, and we're just saying we're essentially creating an instance of the default predictor from Detectron2 with our new model. So now we'll have something that we can give it an image, and it'll return those detections on. Run this. And it didn't take too long to run. Sometimes it'll take a minute if it needs to download anything extra. And then here, I'll walk through this, but we'll just make sure that we are getting our detections. So we got this image, and then it says 99%, and we have a goose in it. Did anyone get to this? If so, you trained an awesome object detector. And even if it was confusing because there's a lot going on, I think you could go back in here, change all those things I was talking about, and build your own object detector with your own data set, which would be really cool. So here what we're doing is we're just getting a test image to feed in and get these results. And then we're using OpenCV, that's CV2, and the function .mread. So we have our test image path. We're giving it to OpenCV. It's going to now read in that image as an array so that we can do other stuff here. And then here, so it basically into the format that it's expecting, that the predictor is expecting. So then we're going to make a new variable called output, and we're going to feed it to our predictor instance and pass in that image. And then the outputs is going to make those predictions. I'll show you exactly what it actually returns in a second. And then this visualizer function is something built into Detectron 2, and it makes it really easy to just output an image like this and draw the rectangles over it. And this crazy looking little stuff essentially kind of slices. What we're actually doing is reversing the colors inside the image array. There's some dumb thing where, I don't know if it's dumb, but it's a kind of annoying. Most people would define colors as like RBG, right? Red, blue, green. But it's OpenCV does it the opposite way, where it's like BRG. And so if you don't reverse the image colors passing back and forth between like OpenCV and other image libraries, then the colors will be off. So that's what this is doing. It's just kind of reversing the color there from the RBG version from OpenCV. And we're passing it some metadata. So essentially what this is doing in here is the metadata. It's not printed here, but this is where it gets like the name of the labels. So it's a goose or duck or anything like that. Detectron 2 has a kind of a weird thing where just their image visualizer, if there's only one instance, like we have in here, we only have goose. It doesn't say the label name because I think it's just like, well, you know what you're predicting. But if you had a goose and duck, then it would type goose here and duck on the other one. And then scale, this just resizes the images. So we're saying display it at half the size instead of full size. And then this is just drawing out. I'll show you what this looks like right afterwards, but this is our actual output. And so this is drawing the output from our model over our image here. Oh, and you'll see this is a CV2 imshow is something we imported at the beginning because CV2, again, OpenCV, has a lot of problems if you just use it in a Jupyter notebook. But Google made their own kind of like library called CV2 imshow, and essentially what it does is it allows you to output a OpenCV image in Jupyter Notebook or in Google Colab. And if you tried to do this, it would usually just be like CV2 .mshow. It would actually like probably crash your notebook, in case you were wondering what that is. And also common error. So if you are using OpenCV and you use something like CV2.mshow instead of something like this, and your notebook keeps crashing, it's probably that reason. But yeah, if you did this, you have a pretty nice little object detector now. And this is what the output from the model looks like. So when we ran our predictor, we got our outputs when we pass in the image, we get this kind of like a tensor or a dictionary here, where it's saying the number of instances. So it predicted there was 2 instances. In this case, we can see that was correct. There's 2 geese. And it has some details about the image, the height and the width. And then fields has pred boxes, so prediction boxes. And inside there we have boxes. And this is actually the coordinates to draw a rectangle. So we were to look at where these pixels would line up. It would draw a rectangle around our goose. So this is super important. This is actually the most important thing is you get this stuff returned. And the visualizer, this is just kind of something neat that's built into Detectron 2 that makes it easy. But you might want to build your own visualizer in OpenCV or do some other stuff with this type of data and not just output here, right? Like you might want to make some other decision. If we add polygons instead of just the rectangles, we'd have another section with a whole bunch of true and falses, because it gives kind of a true or false array out that you can use to then draw those polygons on. And you can see here too, here's the detection scores. So the first one, it was 99.18 certain, and the other one was 98.97% certain. And they were both predicted of class 0. Again, we only have one class, so they should all be zeros. And if you're not familiar with Python or most programming languages, the indexing starts at 0. So if you looked at what all the labels would be, let's say we had geese and ducks, geese would be 0 and ducks would be 1. So in this case, 0 would correlate to goose. And then here's just a really quick example, right, of something you might want to do with that data. Is a lot of times, like, this visual stuff is really cool to look at. We actually might want to do something just like, you want to count how many geese are in the frame. And doing something like this, just print detected, that might already be like a good use case that you want to solve, right? Like, we just want to know how many things are in our video feed, like how many people are standing around, how many things are in our image. Let's run this other example real quick. You can see detected the goose. It also detected all these baby geese. If you look at the labels, these were never labeled as geese, but it did a lot of detections for them, which could be good or bad depending if you want to detect baby geese or not. And to get around this, you would want to train on an image like this with the baby geese in it and have only this goose labeled, and then your computer vision algorithm would pick up, well, these aren't what I'm looking for. But we didn't have any baby geese in the training data. I'm going to quickly kind of just go really fast, like, let's run these other cells just so we get to the end in case anyone has to go, and then I'll come back and walk through anything else. So there are some evaluation metrics. I can talk more about this in a little bit, essentially just to see how good your computer vision algorithm's performing, or network's performing. And here, okay, in this case, we look at our validation data set of 34 images. We see how good it did. And I linked to a good post here kind of reading more about these evaluation metrics, but essentially it's just saying average precision. And you can see here, that isn't a super high score. But I think the reason is because we had like pictures of these baby geese in our validation data set, and these are considered wrong, right? Because they weren't actually labeled as geese. So it could look at this image, be like, wow, like I mispredicted 6 things here, and I should have only predicted this one thing. So I think that's actually why precision isn't super high there, just because it's detecting those geese, those baby geese, as full-grown geese. All right, and real quick, I'll just run through all these, and you should too, and then I'll walk through what's going on. Essentially, this is going to take in a video and run our detection network on that video, and then save a video with the detections drawn over it. So this should start counting. And once you do that, you'll have a really cool video to show off that you built an object detector, like a custom object detector. And when you label your own data set, bring it into Colab, it's even cooler. You can make your own video on whatever object you want. So if you want to detect your dog or plants or anything you can think of, you can do that. All right, so what we're doing here is we're installing a couple more libraries. This is called YouTube DL for YouTube download. We're uninstalling a certain type of OpenCV here because I think it causes issues with the detection we're going to do here. I should have probably just done that earlier in the notebook. So we downloaded those libraries, and then we're going to use YouTube download, and I pass it this URL. Oh, I missed this code, sorry. Should have run this one. Oh, I did run it. So here, this is a part of the URL to this goose video, so we want to run the detections on this now. And that downloaded the video, so now we can actually run detections on it. This is really useful. In this case, that video really isn't that long, and we could run detections on the whole thing. But if you go on YouTube and you get something that's like 5 minutes, you probably don't want to do detections on the entire 5 minutes. So you can do something like create a 6-second clip, is what this is doing from that video that we downloaded. So we saved it to something to an output of video.mp4, and then we're saying, hey, go look at video.mp4, which we can see is right in here, and create a 6-second clip from it, and then call that clip video clip.mp4. And then in here, we have some video parameters that we want to extract. So we're saying we're going to capture that video clip. If you want to do different video, you would just change this URL to whatever your video is. So if you uploaded one in Google Drive, again, you can navigate to where it is, copy on it, hit copy path, and paste it in here. And then here we're getting the width and height of the video frame, so we know essentially where to draw things at. Frames per second, so we know how many frames are in the video. And then number of frames, so we can calculate how many frames are in the video, and the number of frames, so we know that, hey, there's, if there were 60 frames in this video, we're going to take each one of those frames, run it in our detector, get that output from our model, and then draw those bounding boxes for each frame. And then we're going to write out to, or we're going to save that video as out.mp4. These are just kind of some formatting options. We want it to be an MP4. And then here from detector.2, we're using something like we did before, where we did the visualizer, except for this is a video visualizer. And again, we're passing it in metadata. This comes from our test data set, so really what it's getting from this is just the labels. So it's saying goose or something like that. And then this is our run on video function. And we're just saying, while there's still frames left, so we're saying there's 0, like we start with 0 frames read, and then every time we get a new frame, we're going to increase that down here. So essentially they're saying, well, there's frames that we haven't looked at, look at the next frame in our video. And here we can see the output. We get the same outputs variable like we did before, and we run our predictor on each frame. So again, every frame in our video, we're going to run a predictor on. And then we're going to say the frame is equal to this CV2, again, OpenCV function. So we're reading it in, and then we're changing the color from RGB to a BGR. And then we're drawing the visualization. Again, this v.draw instance predictions comes from that video visualizer function that we have from detectron2. And we want to put the frame, so the video, like essentially the image in there, and then also draw those outputs that we saw before, those rectangles. And then this is, again, kind of annoying thing where we're reversing the color again is all we're doing here. And then we're yielding our visualization out of that function. And then we call that function here and saying essentially for each frame, just go ahead and do that on each frame. And then we're going to use a video.writer.write, and that's actually going to stream together all those visualizations. So every time a visualization comes out of here, essentially we take the frame, draw those rectangles to it, and then we make a video out of all those images. Because a video is just frames or images strung together, right? And then we just do this .release, which usually you do on anything with OpenCV, just saying you're done with it. And then this downloads out.mp4, which is what our file was called. And if I open it up, we have detections working on geese. Did this work for everyone? I know there were some TensorBoard issues, but were you able to run the rest of the model? People are saying yes. Yeah, I'm not sure what that TensorBoard thing is. I haven't seen that before. So I know this might have been a lot, especially if you really haven't done a lot of programming before. It could be really interesting seeing all these variables and stuff going around. But I think that if it was confusing, let me know if there's anything you want me to go over again. And then also, just anytime you do anything new, it can be really confusing. And if you can understand kind of the ideas of what's happening, and then go back to it and review the code, or look at it later as you learn more, it'll all usually start making sense. So the most important thing too, really, is to keep learning though. So again, you can download HyperLabel. I really recommend doing your own label, or doing your own labels on your own data set. I think you're going to learn a lot from that. And then also, if you have any questions about labeling or any issues with the Detectron too, because I know especially when you get to more custom stuff, feel free to ping me on Slack. Will be the best place that I can answer, and we can share code. You can also connect with each other and or help each other out, right? And then I have a lot of other links in here too. So if you have the same notebook, you can click here to join the Slack if that one works. If not, then use the one I used in there. You can follow us on Medium. I'm going to be putting up more computer vision tutorials there. You can read and watch that last talk I talked about. If you want to brush up on Python, the Galvanize Prep course is really good. And then also have links in here. So if you want to get more behind the scenes of how object detectors are working, you can go ahead and click these. So you can read kind of these explained ones, are simpler articles that I linked to, like Medium articles, how like single shot multi-box detectors work. And then there's the actual paper, which sometimes papers can be a little like dense and theory heavy. And usually the explained articles do a good job of just kind of breaking it down in simpler terms. And if you want to look at like the official Detectron 2, official Colab, I'll just copy these links in here if you want to click any of these links. And then I'll catch up on chat, and I'll be hanging out too. So if you have anything you want to go over now, I'll do that too. I'm just going to stop the recording real quick.